Okay, so the recording should be going. And so we'll be taking a look at an example here. What we want to do here is we've seen a number of examples where we're dealing with a sort of constant or uniform charge distribution. But let's say we had, and I'll sort of draw the setup as I'm doing it here. Let's say we had a setup where we had some sort of a plate in the plane here. Let's say this is our y-axis and this is our x-axis, and we have a plate that extends from, let's say, x equals 0 out to x equals 3, and from y equals 0 out to, say, y equals 1. And so we have some sort of a plate here like this. And let's say we have some sort of a charge density on here. So we have a charge density. We know that we would write this as sigma because we're dealing with a two-dimensional object here. So this is some sort of a charge density is spread over the whole plate, but it's not a constant charge density. It's not the same everywhere. Let's say our charge density was really a function of x and y. So we had a charge density that's some function of x and y, and we can write it down like this. Let's say it's 2 plus x y squared coulombs per meter squared. Okay, and so what's this kind of going to look like? We're going to end up with a sort of lower charge density here. And a higher charge density over here, right? Well, let's say we were interested in the total charge. Let's say we named it. Let's call this Q. Let's say we were interested in the total charge over this entire surface, right? Normally, what we would do is just find the area of this surface, right, and just multiply it by our charge per unit area, and we would end up with our answer. So normally, if we had or I shouldn't say constant, I'll call it uniform. So we had a uniform charge density over this entire surface. We would just say that the charge is equal to our charge per unit area times the area of the surface that we're looking at. Okay, but in this case, it's not quite so simple. In this case, we need to integrate over the entire surface. So what would we end up doing, as we've done a few times in the videos that I've already put out for chapter 21, we're going to break this thing up into a bunch of tiny little tiles, integrate over all the tiles, and find the total charge on this thing. So I'm going to kind of set it up here. Let's say we set up just some line here. We're going to call this x, and then we're going to add some tiny little dx to it, some tiny little extra area. So this would be x, this would be dx, and we do the same in the y direction. So it's going to end up being like a two-dimensional integral here. So let's say this was y, and then we added a tiny little dy to it. So this is y, the tiny little thing is dy. And so we're going to integrate over the whole range of possible x values and the whole range of possible y values, filling up these tiny little tiles of area dx by dy. Okay, so that's sort of the plan. That's how we're going to try to answer what the total charge on this surface is. And so the way we're going to do that is we're going to start off by building these tiny little chunks of charge, because each of these tiny little chunks of area is going to have some tiny little amount of charge on it, right? So normally we would end up with Q is equal to sigma A, right? But in this case, we want some small amount. We want some small amount of Q, so some dQ, and it's going to be equal to sigma dA. But we've broken up our dA into tiny little steps in the x direction and tiny little steps in the y direction, and so we end up with sigma dx dy. Okay, and so the plan here, as I sort of talked about in in the videos, and I'm going to talk about in the example that I'm going to do on Wednesday also a sort of two-dimensional integral that we're going to do to redo the disk problem from the notes. But starting from here, so we've already set up the element that we're going to want to integrate over, and now we just need to set up the integral. So what we want to do is we want to find q. Q is going to end up being and I have to be careful how I've written this here. Okay, so this is our dq, just to keep that in mind. So q is going to end up being some double integral of our dq. Okay, and the way we're going to write this is going to be, we're going to integrate from y equals 0 to y equals 1, from x equals 0 to x equals 3. Then we're going to integrate our sigma, which we have up here. So our sigma looks like this. And we're integrating in the x and the y direction, right? And so that's the integral that we need to do. And so I'm not sure, again, how far you guys have gotten in your Math 112 classes. Some of you have already done Math 112. I'm sure some of you are working through it right now. But I'll go through the integral in case it's not sort of obvious how to do this. And so the way we would do this is we would start by doing the first integral. We have to be careful. We can let some stuff flow through the integral, and some of it we kind of can't, right? So let's take a look at how we would do this. The way I would set this up is I would just wait to do the y integral until later, because we have a number of things that are going to depend on y first. And then I'm going to break up these two terms into two separate integrals in x, right? So I'm going to, for the first term, I'll factor out a 2. Then we're going to integrate x from 0 to 3. And the only thing in the first term that is x dependent is dx, so we're just going to have dx there. And then for the second term, we can factor a y, our y squared, out of the integral, because we're doing an integral in x here. So we're going to have x equals 0 to 3. We're factoring out our y squared. And then we just have an integral of x dx, okay? And then after this is all done, we have to integrate in y, okay? So let's kind of do this really quickly. We're going to end up having still our integral in y. Then on the inside of the bracket, we're going to still have our leading factor here of 2. If we do this integral, I'm going to kind of do it all in one step. The integral of dx is just going to give us x, and then we need to evaluate x at 3 and 0. But 3 minus 0 is just 3. And so that's going to end up equaling 3. And for our second integral, we're going to have, well, we still have the y squared left, but we're going to do the integral. We're going to start off doing the sort of indefinite integral. I mean, the way we think about this is we do the indefinite integral first, and then we come back and we feed in the limits that we want to look at and sort of see how it looks, right? So the integral, the indefinite integral of x dx is going to end up giving us 1/2 x squared, right? And we're interested in the limits 0 and 3 here. So we'll evaluate those in the next step. And then once we're done, we would still need to integrate this over y, right? And so writing it down one more time, we're going to have y equals 0 to y equals 1. These two terms obviously are going to combine. We're going to end up with a 6. And then we have our y squared left over. And if we evaluate this, well, if we evaluate it at 0, it's going to be 0. So all we're going to have left is the 3 squared over a half here, or over 2, I should say. So we're going to end up with 9 over 2 dy, okay? And now we're pretty much set up to do the y integral, right? And so the way we do that is we can break it up again into two separate integrals. The 6 is going to come out front, and so we'll end up with a 6. The integral of dy from 0 to 1. And then a similar situation for the second term here. We're going to have plus. We can factor out the factor of 9 over 2. We're integrating from y equals 0 to y equals 1. We have y squared dy, okay? And if we do that, I'm running out of space here a little bit, but I can just add a page. So we'll end up having, we're going to end up having this integral from 0 to 1 of dy. Well, we're going to end up with with 6, and that's going to end up giving us just a 1, right? Because dy is going to integrate to y, and then we're going to evaluate y at 1 and at 0. And so at 0 we get nothing, at 1 we get a value of 1, and so this is just 6 times 1. For the second integral, we have this leading factor of 9 over 2. If we do the indefinite integral first, we end up with 1/3 y to the third. And this is just both of these are just using the sort of power rule in reverse, right? And you probably will have seen this in your Math 112 already, but if you haven't, it's just the power rule kind of working in reverse here. And then we have to put our limits of integration on here. So we have a 0 and 1. And at this point, it's just a matter of simply cleaning things up, right? We end up with a 6 plus 9 over 2, and then we have just a factor of 1/3, because basically we're substituting in this 1 cubed just gives us 1, so we have a factor of a third, and when we substitute in the 0 we get nothing, right? And so if we clean this all up, we're going to find that we end up with a 15 over 2. Okay, and so that's kind of our answer. Our Q is equal to 15 over 2 coulombs. Okay, so that's how we would find the total charge on this plate where we have a density, a charge density that isn't uniform. It is dependent on both of our coordinates, x and y. So let me just stop the recording here for so that we can save this.